let's start. So we are all tired. It's a good. So you have to stay awake. I will not have difficulties to stay awake because I am standing. I never sleep when I stand. You may have difficulties. So I will try to motivate your attention by asking you questions, and you will have to try to answer. Okay? So I'm going to talk about the hydrology of ungauged catchments, which is a very interesting subject and also a very difficult one. Ungauged refers to calibration, and calibration can be done. Dr. Samuel-Martin learned calibration on such a tool. It was wonderful. He was solving many problems by turning slowly all those small things. That way, it was good times.
Oh, it's Russian, in Russian, so it's a Russian tool.
It's a Russian tool. It's a Russian tool. I am adapting the presentation to the place where I am. So now we will talk about the calibration and about the lack of calibration. But I wanted to ask you, who already calibrated a model manually? So some of you did not.
Ludmila did not. She calls it tuning. She avoids the term calibration. She
Yeah.
says it's tuning.
Yeah. She's not calibrating. She's looking at the other hydrologists from the top and saying that she's physically based. She does not need to calibrate. She just tunes. I know this story. But it's not her fault. It's the fault of her advisor.
Not the fault, it's opinion.
Okay, so who wants... I want to volunteer, somebody who never calibrated among the students, to come and calibrate. No, calibrate she cannot. Her hands, the fingers will burn immediately if she tries to calibrate. Or she would be burned by her advisor upon return. I wanted to show my colleagues, they were doing plans to... I'm always criticizing them that the tools we use in class are not good enough for the students, that they are too complicated. So, and they produced this as for hand calibration. I need somebody to come and calibrate a model. A volunteer. Somebody who has heard about calibration but not tried yet. Somebody who has had a dream about calibrating a model but who had not fulfilled the calibration. Давайте. Give me any...
They are not sleeping because of us.
No. Okay. What is the most common Russian name?
Maria.
Maria? Is there a Maria here? No,
I have already calibrated the model, so I don't have it.
No.
Then, Svetlana? Is there a Svetlana?
No.
No? Do you want to come to calibrate? Yes? So this is a French model, but it has nothing to do with the fact that it is French. Here, what you see is a hydrograph. In black, there is a hydrograph. This is a measurement. And since this is a very simple model, we just want to reproduce the hydrograph. And the hydrograph here is in red. And you have, and it's a lowland basin. Lowland means that there is not a lot of snow. And you have 4 parameters to change. And those parameters, they are related to the structure of the model. The model, I will help you, I think. So the model, it's named GR4J. You can change, but let's not change. And I think there is a model diagram there. that tells you that how the computations are made, of course, and there is basically it's very common for conceptual models. You have stores. The stores represent the memory of the catchment, the memory of the soil and the aquifers, and there are two stores. One is the soil moisture accounting store, but we call it production. We try to give non-physical names, because if you give physical names to the model, you will forget after a while that it's just a model. You will think that it's a physical reality. So to do that, we on purpose we don't give physical names. And you have precipitation, potential evaporation, you have interception, and then you compute based when the production store is full. Then you send all the precipitation to the river. When it's dry, you keep all the precipitation there. You evaporate from there. And then you have two routes, a nonlinear one and a linear one. You understand? I said nonlinear, linear. It's because it's a mathematical description of the model. It's not a physical one, because it's you have all seen catchments. It's a very, very simplified representation of the catchment. But it's a simplification that works well. And Svetlana, you have those. No.
Женя.
Zhenya. Wait, I said Svetlana. Why?
No.
Freudian slip.
Okay. I was sleeping. Oh, sorry. Zhenya is going to move those 4 parameters and to see whether it has an impact on the hydrograph. So let's go. If you move them, will you see something, by the way? You have to move them, you understand, okay? For example, and then it is supposed to compute, and you see nothing, though you have to go to the, not to the model diagram, to the time series, for example. And then, what did you do? Move. So you don't know the meaning of the catchment. This is, in all the catchment model, there is also there is always a parameter that is responsible to for the water balance. People try to sometimes calibrate a parameter on potential evaporation. People calibrate on precipitation. Here, in this representation, it's a leak. We consider that. Wow.
So PhD, French PhD.
So this is a unit hydrograph. It is just switching. Do you see what it does? It is taking the flow there. Then, okay, if this is positive, it means that the catchment is gaining flow from a neighboring catchment. If it's negative, it means that it is losing water to regional aquifers. Genia, you are very good. You have never done that, or you have done that all your life. I think I'm sure your colleagues are lying.
It's a Russian hydrological school. You know.
That, yeah.
Advanced education, fundamentals.
Yeah, wonderful skills. So if she has done it by the eye. Okay, she has calibrated the model. We could also look at other plots. We could before that. Did you already push before running the automatic calibration? You could also, Genia, if I may suggest, look at this plot, which is model performance. So in this plot, what do we show? We show again the hydrograph, but we show some synthetic plot, which is, this is the regime. Regime, it means long-term average monthly stream flow, the regime of stream flow, and you can try to also to fit better to that. You can see that in January and May you are a little low, you are too high in there. Then you have here the courbe des débits classés, the distribution of flows, and here you just have a very common plot simulated flow versus observed flow. And you can look at all of those and also at the hydrograph to try to get better results. So this is what we called multi-objective calibration. Look, are you looking at the regime plot? Because you have, it's almost perfect now. And you have improved a lot the distribution, the distribution here. And here you can see that you are still a little biased for a very low flow, but for most of the distribution.
Autumn and winter discharge is a little bit high.
Yes, but it's interesting. Okay, so what do we want to demonstrate with this? We don't need. Calibrating is not extremely complicated. You can do it by hand, especially if somebody has written a nice interface. It helps. You don't need to compute criteria. You can do it by eye. You can do it by eye. You can also do multi-objective calibration with your eye because you can look at different plots that tell you something different about your simulation. You can compute numerical criteria, so they are in the upper part. So what do we have? This is Nash and Sutcliffe criterion on the discharge value, 0.6. Nash and Sutcliffe on the square root of the discharge, on the inverse of the discharge. Why do we have all those? What do they produce as information? Why? Sorry? The reliability. It's not really the reliability, I will say, because the reliability can has a status. The quality. And we want to have it as high as possible. Okay? And we could try to do multiple objective also on several. And why do you think we chose to add a transformation? Is it something you do? No? Okay. So it's basically we look at the formula, you will see that when you get the inverse of discharge, you put a lot of emphasis on the very small flows. On the opposite, when you compute the root mean square error on the flows untransformed, you put a lot of emphasis on the large flows. And square root is intermediary. KGE is the same basically than the rest. It's a small modification. Okay, so we could have looked at those. And now, Zhenya, not Svetlana, will push on the run button and ask for an automatic calibration. But first, you will need to tell the model which of all those criteria you want to maximize, because we are not able to do multi-objective calibration with that. We have to choose one objective. What do you want? You choose. On discharge or untransformed. So you push run.
Wow, you were very close.
And we can see that you were very close, and if you go a little up, what was the value, the optimal value? 0.81.
Yeah, it's really improved.
It's big improvement. Yeah. But look, Zhenya, if you look at this plot, bring this plot a little up. And if you look at this plot too, we see that we are overestimating the very low flows. We don't see that here because it's not in log mode. So we're overestimating. What could we do to try to solve specifically this issue? Maybe the model is not able to represent. That's one first possibility. Or, to be more extreme,
Okay, then inverse.
Inverse. If you try the inverse, let's see if the inverse will improve this and possibly decrease something. So if you choose objective function inverse, Nash and Sutcliffe on the inverse, and you push run, you see that it's perfect. It's wonderful here. It's not wonderful there. And we were 0.7, now at 0.81, we came down to 0.8 because we improved this. Okay? So, an illustration. This is I am not in love with the model, but I like it very much. But it's a model that is not able, on this precise catchment, not able to be perfect on high flows and low flows. It happens a lot with models. Okay? So what did we see? We saw that calibration has produced values which are optimal. So you have two values for the production function, that compute that amounts of water that will in the flow, and two for the function of the transfer, for the transfer function. Okay, this is the typical model calibration. So I propose that we all upload Genia. In fact, why did I do that? Not to show you that my colleagues are very good at making interface, but because I just thought it was very strange to start talking about calibration and not touch the calibration of a model. Especially that now we are going to speak about the lack of calibration. So this is a model that the person who taught me hydrology, he started maybe 35 years ago. His name was Claude Michel. Oh, he's still alive. He's Claude Michel, but he's retired, and he don't want to hear about hydrology anymore. And in his first paper, somebody said you should read the first paper. You cannot read the first paper because it's in French. He published it in France in '83, and the question was, what can you do in hydrology with a single parameter? So he was basically a mathematician. He was looking at the rainfall runoff transformation, not from a physical point, but he was asking himself the question, I have two signals, and I want the simplest possible representation of the transformation, mathematical transformation. Now, he worked all his life on calibration, of producing a model that would be easy to calibrate, that would be fast to run, etc., etc., etc. But now, when you are in front of an ungauged catchment, you are working for a consulting company, and a question is asked to you about a catchment. We want to build something, a dam, or we want to do anything. You are the authority in charge of authorizing releases of water from any kind of station. You need to know what kind of discharge there are there. And that's where your problems come, because what we did with Genia did excellently is she moved the parameters to try to match the observed discharge. And we cannot do that, so where do we take the parameters from? So this is, by the way, while preparing this is all the gauging stations I studied for my PhD. I found this picture, they were very fond memories, and basically that's to tell you all those gauging stations, they are not there, you can't use them. But an ungauged catchment, so we do not have stream flow, but it does not mean that we know nothing. So we may have a lot of information. So rainfall we may have. Why do we have rainfall on ungauged catchments? Yes, because contrarily to stream flow data. Stream flow are very continuous in space, so we can try to interpolate them. And if we cannot interpolate them, some people tell us that we can use radars. Of course, they are lying, those who sell us the radars, because if they don't have the point rain gauges to calibrate the radar will give extremely approximative information. So we still need, even if we have the radar, we still need the rain gauges on the ground. And if we have nothing, there are satellites that are giving a very approximative information, so low quality. But if you have nothing, it may be better than nothing. Okay? Then what else do we have? We have digital elevation models, and we all like to use digital elevation models. First, because they produce beautiful maps, and then because they bring us the most important, the possibility to draw the catchment, to know its size, to know about the slopes. They bring a lot of information. We have vegetation maps. We have geological maps. We bring us some information. Extremely difficult. Oh, this is France. Sorry. Extremely difficult to turn into quantitative terms. We have qualitative information, but some of us know to. We also have drainage density. What is drainage density? Geographers. This is geographers love.
Length of streams per area?
Length of stream per area. Okay? So it's expressed in kilometer per kilometer square. And here, because this is almost a drainage density, it's expressed in kilometer square, we took all the blue lines that we find on French maps, which mean rivers that have been mapped by, and we ask ourselves, what size of catchment do we have above all those blue lines? The size of the source. It has another name in digital elevation model. We call it source area. I forgot. So it shows you that here, I mean, this is not. There are places where there are almost no blue lines, no desert. In fact, those are the areas in France that are the most permeable. So you have no water running, no rivers on the ground. Everything goes in the aquifer. And so we have here the choke area that we were discussing the other day, like in the UK. And we can see many specificities. So that's interesting. Again, that's information to have on maps. Oh, I forgot. We have also soil maps. And I took these soil maps from the UK. They have hydrological classification even of soils, host classes. And so now, with all this information, we should be able to do something. And now there are two classes of things that we can do. We could try to take the problem at the root and look for fundamental solutions to improve the model and create the model that would not need any calibration, not even tuning, Mrs. Lebedeva. Okay? So, and for this model, we are just waiting for either the return of Newton, Galileo, and Einstein, or for you. So that's your job. I don't know how to do it. Of course, I thought I would do it. I never did it. So, or we can look for acceptable solutions, acceptable from the point of view from the of the user, of an engineer, that would like to provide answers to the questions that are asked to him. So they are just solutions. They are not the fundamental solutions we all dream of. Okay, and I'm not defending the fact that instead of repairing electricity, we bring electricity from somewhere else. But sometimes it helps. So the first of those acceptable solutions that I see, it's regressions. We all know what is a regression. And if I call x, for example, we used to call our parameters not by name but by number, x1, x2, x3, x4. Okay? We can try to reconstruct those based on empirical relationships. Empirical mean that I will try many descriptors from the literature, from the maps, and I will try to find the best fit. So that has been done for a very long time, and that's what. And it has been done with the hope that we will produce beautiful relationships, beautiful fits, R² of 0.8 or more. Typically, when you try to do that, when I try to do that, I get correlations. When I get the correlations of between 0.1 and 0.2, I am happy. So they are very low. Okay. So it does not mean that the model will not work, but I can say that the relationships give very low correlations. Another way, if we don't want to do that, would be to try what we call regional calibration or group calibration. So we say that we are on an engaged catchment. I agree. So we cannot calibrate. But we are in a region, the catchment has neighbors. So if we are in a rich country with a dense hydrometric neighbor, we have neighbors very close. If we are in a poor country, neighbors are very far. But we can always find neighbors. And by the way, the notion of neighbor, or what is a neighbor, it's not necessarily only the geographical neighbors that we should think about. We could also imagine that a catchment has neighbors in some physical space, in some similarity space. Like we could have people from people looking like each other that come from very different parts of Russia. They will still be similar to each other, even if they are not physically, geographically neighbor. And then if we can gather enough catchments, we can try to calibrate a single parameter set for all those catchments. And we will call this parameter set the parameter set representative of this group. And then we will have a parameter set and we will transfer to the ungauged catchment within the same group. For example, what could we do? We could try to take all the simplest thing is with the area, catchment area. We could rank if we have a large data set of hydrometric stations, we could take the small catchments, a mid-sized catchment, or a large catchments, and see whether there is a common parameter set that will fit with all the large or with all the middle. And you can do that with any characteristic you like. And that's also interesting because in geology we don't know how to turn the geological information into quantities. We can still consider similarity. We can say all the catchments that are on granite or chalk and so on. That's a possibility. The third possibility, which is I consider the most widely used. It's the one I use while waiting to find better solution. Is parameter transfer. Parameter transfer. It means that you will take a parameter set and transfer it between neighbors, and of course neighbors, either geographical neighbors or physical neighbors, similar one. So how do you do? We have a target catchment. It's engaged, but we have identified a given number of neighbor catchments. Here 4. On these catchments, we have been able to do a calibration of our model. So we have 4 parameter sets. Each color corresponds to the neighbor. And what we will do, we will do a simulation of this charge with each of the parameter set. And then we will average we'll get an average of these 4 simulations. Average, it can be simple arithmetic average, can be weighted average given to distance or so here the example. So this is the target. These are the 1, 2, 3, 4, 5. Sorry, here there are 5. There are 5 neighbors. So this is in France. For those who recognize French rivers, this is the Loire, and this is the Allier. Basically, we produce 5 simulations here, and these are the simulations that the model GR4J here has produced. And at the end, I take the average. It's extremely simple too. So the question that you can find in the literature, you could ask yourself is, why should I do 4 or 5 simulations and then take an average? I could have done it with a parameter, and I could have saved me it doesn't take. The good thing with those models that get calibrated, it's usually they're very fast to execute. So you never have a problem of computing power. But again, when we learn mathematics, we are taught to be lazy, to look for the simplest solution. So why should we do something more complicated? So basically, there are 2 options. We could average parameters, or use the parameters as they are and average the flow simulations. So I prefer this one. Why? This is a question. It preserves the physics. You are very nice to use this word. I'm very. It's embarrassing. No, we do. I agree with you. But some people here, I'm not going to show them or to look in that direction, think that those conceptual models are an insult to physics. So
Yes, to some extent, small insult.
A small insult, yeah.
But wouldn't lead to jail. So just offense on the street, but not hitting hard.
Okay. So why is this approach? What is wrong in averaging parameter sets? So, just to remind you of my question, here, instead of producing here 4 simulations, I could just have taken a mean parameter set, so a mean soil moisture counting store, a mean leakage parameter, a mean routing store, and a mean unit hydrograph. And I could have done 1 simulation. Why isn't that good?
Non-linearity in response. Non-linearity in response.
Non-linearity in response.
Result is unexpectable.
Results unexpected.
Unexpected.
But why?
You don't know what to expect from an ungauged catchment.
No, and you don't. You are not allowed to. You don't even look at those models. So
because like maybe it's all experiments just taking big areas, and your catchment can be like just not the typical of this area. So it's like the big parameter to be for big area. This small catchment that we just don't know anything about it can just evolve in like different soil type or something that is going to break your model.
yeah, but remember that we took geographical neighbors, but we could have grouped them by similarity. We could have done a more physically, let's say, interesting approach. Take regrouping.
Form and size of catchment.
Excuse me?
Form and size of catchments.
Form and size. But if we had chosen the same form, the same size, again, it's a more mathematical problem there.
You could lose water.
There is some combination. So
They
the parameters are used in some combination.
Oh,
In
Yes.
They're correlated.
They are correlated. So we do not want to build models that have correlated parameters. But unfortunately, when we build such a model, there are some correlations between each other, which mean that x1, if I add 10% here and remove 5% there, I remain around the optimum. Okay, we can also say that there are compensations. In this model, which has been written by a good mathematician, not me, but there are very little compensations, but there still are. Okay, and the other point is the more heavily parameterized your model will be, the chance that the compensations are more and more important are larger. So that's why that it's always better to use parameter set as such than to break it into parts. Okay. And so we did some comparison. In fact, this is my colleague Ludovic Houdin from Université Paris 6, who did most of the work with us. He used to work with us before, and it's already old work. It's almost 10 years, but we did not find. We tried a lot, but we did not find very new solutions. So what is written there is still quite valid. But now, it's when we look at the solutions for ungauged basins and we look at the performance, usually there is something obvious. It's that there is a big drop. We lose a lot when we use models that require calibration in an ungauged basin. We lose a lot because there is a lot of information that the discharge carries in itself and that we don't have access to. So if I am a professor at Moscow State University, I could imagine, for example, I have students, and if I need to work on some catchment in Siberia, I could send my students in summer camp or winter camp. And
The word camp and Siberia.
the word camp has no. I'm not using the camp in this acceptation. Field work. And I could imagine send a couple of hydrologists to make one measurement. Okay, take boots, enter the river, measure the speed, and you have all done a discharge measurement. So it's not complicated. It's just time consuming, but it's not complicated. As long as there are no ice and no crocodile in the and I could have one point. If I send two groups of students, I could have 2 points. If I send them over several years, I could have 10, 20 points. That's a possibility. So the question is, does it change the situation or not? Is it worth to send my student there? And the idea would be to then calibrate just the model with just a few measurements. So, is it mathematically possible? When I calibrate, I minimize. More or less, I will minimize a criterion, and the criterion, it's something like the sum of the we could have Okay? It's the Nash and Sutcliffe criterion. It's 1 minus that divided by a constant. We could transform the discharge again. It will not change. It's something like that. It's a sum of squared errors that we try to minimize. Okay? I do that. I compute this sum for all the time steps from 1 to n. Did anybody say that n needed to be at least 3,650? No. It's 1 to n. Can we do that with 1 to 2, with 2 measurements? Does it make mathematically sense? Yes, it makes sense. Even with 1 measurement, we can compute a criterion. Then the question is, if it makes mathematically sense, we should ask ourselves, does it make hydrologically sense to trust 1 measurement to calibrate one hydrograph? Maybe not. 2, maybe not. But you understand, there is still some information, and the idea would be if I have 0 measurement, I'm in the case of an engaged catchment. By the way, I showed you a method for an engaged catchment. Not very good, but the only one I can propose. If I have 1, 2, 3, we should be maybe able to find an intermediary solution. And basically, that's what we propose to do. So we have this neighborhood approach, and this neighborhood approach will provide us a list of parameter set. I have the following potential parameter sets in my neighborhood. Maybe that this sum could help me choose in the neighborhood. Maybe the most similar catchment is not the closest, but the second closest, the third closest. That's the idea behind this method. So here I have a small number of point gauging. I want to use this information. I know where I am. Here I'm in France. Often on my plots we are in France. And those are the closest neighbors. And I want to use this information. And basically the simplest method I can propose is a method based on the combination of ranks. Ranks. I rank the model. I rank the catchments from the closest to the furthest. I rank the parameter sets. The first one will be the one that gives me a criterion exactly here equal to 0, and I have 2 rankings, and I can combine them with a weight, and the alpha there is a weight, and define a new ranking. Okay, a ranks of ranks. And then I can apply, once I have the first, in the new ranking system, the first catchment, the first neighbor, the second neighbor, the third neighbor, I can still produce simulations, average simulations, and have an engaged, a simulation for my engaged catchment. Okay, so we need to decide how many neighbors we keep. So that is largely model specific. We made tests for 2 models, so ours and some top model, and we find slightly different numbers, 7, 9. And the only thing that we need to decide is what this mixing parameter alpha, how will we decide of its value? So here we have made a test on a large number of catchments. Of course, these catchments are gauged, so we deal with each one as ungauged, and then we verify our computation. Here I am in the situation of I have only one measurement. Here, this is the value of this alpha. Here, this is the value of the average criterion. This is consider it's Nash-Sutcliffe over a large number of catchments. Okay, and we want to be as high as possible there. And here we have moved this alpha. Okay, this alpha. Oh, I had an animation. So if I am here, I am trusting the regional method. If I am here, I am trusting the one measurement I have. What will you? Obviously, if you only have one measurement, trusting it will not give you very good results. And you can improve your results if you trust also the regional information, and then there is some optimum in between both. And if you test, if you have the number of points that you or student groups that you sent, you see that the more information you have, the highest the value of the local information will be. And if you have 3,650 10 years of daily measurement, you will be in the same situation as you had a gauge catchment. Okay, and so we just looked at the optimum alpha. Here, that's sorry, it's French. Number of measurements. The optimum value of alpha. You can see that when we have very little discharge measurements, then better not to believe in the value that we have measured. When as soon as we have a lot of them, it's better to only trust what we have measured. It makes sense, and then we can find a curve that runs through those points, and we can parameterize it. So we can provide in the method even of course it will be model specific. We can provide the weighting factor that you need to use the method. So now I wanted to show you some real results, but there is an animation. So on this graph, so I will show you the average criterion on many catchments. So I will try to have better efficiency. So alpha will vary between 0 and 1. So alpha equals 0, we don't have any measurement. No, n equals 0. It's n between 0 and 50, I think. N equals 0, we don't have measurements. We are in the completely ungauged situation. And there we have, and we have two reference, the lower, which is ungauged situation, the upper reference, which is a gauged situation. And what do we find? We find some kind of curve like that. Did we expect it? Is it logical? Yes. The more information that we provide to the modeler in terms of point gauging, the closest we get to the entirely gauged situation. So we're happy. It's a solution that can work. The only problem is we had a puzzle for several years. We were obtaining that kind of curves, and we thought that there was a mistake in our computation. So here, those curves, I remind, we can have Nash on the discharge, Nash on the square root of the discharge, and Nash on the, here it's a log of the discharge, so with a focus on low flows. And we can have two models. I don't need to give you the name of the models, it's not relevant here. And again, we were varying the number of measurements. And we had some paradoxical situation. What is paradoxical here? What did we look at? We were looking at this plot just before. And we said it's a perfectly normal plot. but I found paradoxical things, especially in low flows. We
Some measurements are better than gauge.
yes. So remember it's on a large number of catchments. So it's on average, it's better to calibrate with 25 point gaugings than with 10 or 20 years of data. That's paradoxical. It doesn't make a lot of sense. Okay, so we found that, and we decided that we had a mistake, and then we gave up. And a couple of years later, we asked somebody else to do, some other students to do the computations, and she found exactly the same results. So we said, it's usually we don't do twice the same mistake. And in fact, we thought about what we do, and we came back to this situation. What do we do when we simulate? We are making a kind of ensemble simulation, because we have 5 simulations, and then we average it. So when you do that on low flows, the low flows being something that is extremely difficult to simulate, that usually is more difficult, because when you make small errors in absolute terms, they can become very large in relative terms. The model is more happy with smoother low flows, and this ensemble simulation and the averaging process is producing much smoother low flows. The models like smoother low flows, and this method was producing smoother low flows. So it does not, there is nothing revolutionary there. It's just another way to show that we should be modest, because if that kind of on the performance of on our models on low flows. For the rest, the situation is seems very logical. But on low flows, sometimes producing several simulations and averaging them will get smoother. Will always get smoother hydrographs, and criteria are like smooth hydrographs.
Surprisingly, the errors cancel out, right? So it means that the equal amount of models show, equal amount of parameter sets show higher flows than there are in reality, and the same amount of parameter sets show lower flows. And the error cancels out and flattens the whole discharge hydrograph.
Yeah.
This is surprising a little bit.
Yeah, I think you're right. What I don't, in fact, what the problem is that I'm averaging many 500 catchments. So it's on the average. On the average, if you want to, if you are averse to risk, you prefer not to take smoother thing and to mix and to make multi models. It's a kind of a multi-model. You are just averaging. But it also means that the model probably has large difficulties with low flows, because if it had not, so are we finished?
We still have 20 minutes.
We still have 20 minutes. Because I can keep going for several hours. About hydrological distance, we were asking. I wanted to ask you before. No, I can show you this. I wanted to ask you when we said let's consider the neighbors in geographical space. How do we compute distances between surfaces? Because a catchment is a surface.
Give a hint.
I given hint. There is, and it is a problem. It is a problem in several. So people usually, in the past, very often we have the position of the gauging station. So we say the distance between the catchment is the distance between the gauging stations. Okay? So we can see that here, in situations which are comparable, it will give very different results. Of course, as soon as we are very far, as soon as we are in the middle of Siberia with almost no gauging stations, we don't have problems. This is a problem of rich countries. So here we would have to have this distance and this distance equal, and here we don't have it. So if the gauging station is not a good indicator, we could take a more average indicator, which is the center of mass of the catchment. Okay? Here, for example, it will solve the issue. Perfect. But here, now look at those nested catchments. There is a large one and two small ones. The large one has a center of mass here. The small ones have the center of mass here and here. What is the neighbor, the closest neighbor of this small catchment? The big one. And if I ask you, I want to transfer parameters, where should I take the parameter, here or in the huge? What would you advise me as hydrologist? The small one. There is more chance that this one will be similar to this one than to the rest. So that's where we need. So in fact, I don't know if all the world call it gauge distance. It's Lars Gottschalk calls it gauge distance. So there is one possibility is you put, let's say, you choose either random points there and there, and compute the distance from one to the other to all the points from there of catchment A to all the points in catchment B, and then you get a distance of surface. And if you want to do very quickly, you can do this, which I call hydrological distance. It has only the name hydrological because I decided it. But in fact, I tried to see whether there would be a combination of those two distances, centroid and outlet, that will give a little better results when transferring. And giving, obviously you prefer to give more distance to the centroid, but giving a little bit of weight to the distance to the outlet allows you to turn those two catchments very far from to further them from one another. Okay? So those were practical solutions for dealing with ungauged catchments. With practical solutions, I think they are really useful because we are lost when we don't have calibration. We cannot rely on calibration. But does it mean that calibration is evil? That's the question I ask you. So, do you know who this god is? Janus. Janus has two faces. And I think that calibration is like the head of Janus. It has two faces. On one side, we could say that calibration is evil because it forces us first to limit our models or to limit our simulations with good performance to gauge catchments. Somebody said, when were we discussing the fact that we need to trust data? Was that yesterday? Some people didn't want to trust the data. And many modelers don't like to trust the data. But as hydrologists, I think we should trust. We have no choice. But we have to trust. We rely on streamflow data. And in one case, don't remember that if there are errors, large errors on the streamflow of one catchment, and then the meaning of the parameter set that you can extract from it by calibration will be very limited. And if you transfer it to a neighbor catchment, we will Will we save the ungauged catchment, or will we poison him? Maybe we can poison him. If we keep in our data sets toxic catchments, we can poison the neighbors. And then some people think that calibrated models are inesthetic. I don't agree, but some of them think. And some of them say that as long as we will keep calibrating, we will not work on real models that are really, truly physical. And this is a sentence that I find very funny. I totally don't agree with it, but many people agree with it. They say that if we use calibration, we may obtain good performance, but it will be for the wrong reasons. I have never understood how you can be right for the wrong reasons on one case you can be, but when you repeat the experiments, when you use large databases, I don't know what it means, but several people have told me that. So it's a critic. You have to accept it. On the other side, I think that calibration is not evil because it allows us to build models of intermediate complexity. So the model we used, it was, we could move, we could do the computations in real time and visualize them. I think as a learning tool, they are very good, and also as engineering tools. We can set up models rapidly. Don't forget that if a model is not complicated and we need to complexify it, it will be very easy. If a model is extremely complicated, changing anything is a major issue. Then the calibration allows us to make tests, which are, from a scientific point of view, we often say validate. Maybe it's exaggerated to say that we validate them, but we can test them rigorously by split sample test. I calibrate on one part, I test, validate on the other part, I exchange. I can test the robustness. If you don't calibrate, you don't ask yourself this question. When you ask to a purely physically based modeler, I mean, somebody who does not calibrate and who does not tune either, is your model robust? He or she will answer you, yes, of course, it's physical. Can you show it to me? The answer will be, I can show you the equations. That's the only justification. The justification lies in the physics, in the equations. While you can, to some extent, justify your model by showing that it's robust, it has good performance. In comparison, good performance not in absolute terms, but comparison with alternatives that you can think about. And sometimes, okay, this is dangerous. If there are errors in your model, calibration can compensate for those errors. Of course, it's so. This was the first conclusion, and I had these wonderful citations. So nobody reads Ludwig von Bertalanffy anymore. Maybe in Russia, he was a Viennese scientist. He wrote a book on systems theory. So, and it's complicated to understand this citation, but it's certainly it basically means there is no shame in starting simply. You will have the whole your life to making things more complex. And this was a French author from the beginning of 20th century, that Henri Michaud. No, he was not French; he was Belgian. That was telling that discussing that if we are too contemplative, we will never act. And in some case, we need to act, especially if we are thrown into the water. Second conclusion, I have 5 minutes.
We started.
No, but because after that, I have plenty of bonuses that I am not going to use because there is no way in using bonuses with people which cannot follow. So this is a question for Professor Solomatin. The second conclusion will be based on Soviet wisdom. So you did not see Soviet times. And Soviet wisdoms had to do something to do with this tower that you must recognize, Professor Solomati.
The color is red. Maybe this relates
No.
to Soviet Union, but the rest.
That was in one of the capital cities of the former Soviet Union. It's a radio tower. And it has to do with Soviet wisdom.
Yerevan?
That's
Radio Yerevan.
So we could ask.
Что делать, если вдруг захочется работать? Полежите часа два, само пройдет.
I didn't get it. Say it slowly in Russian. Okay? So, don't forget that I have an Armenian grandfather, so I got very interested in Armyansky radio. And don't forget also that there is a famous paper by Klemesh, who was a very bright scientist, who starts with a Armyansky radio joke. You should read it. So we could ask the Armenian radio the question, and probably we will get an answer. And the answer will start with, in principle, yes. But my answer will be, then, in principle, yes. Calibration is evil because it allows us to reach good performance, produce nice simulations, but perhaps for bad reasons. While its absence will very likely allow us to reach poor performance, but certainly for good reasons. That could be Armenian radio wisdom. Okay. And then I had challenges that can take us for several hours that I'm not going to discuss. I will leave it on this good note.
Before we make an applause, could I pose one question, if I may?
Yes.
Ungauged catchments. The attempt or temptation is to make them gauged, right? Because if you have gauges, then you could do better modeling and achieve become happy. So, question then is for the audience also, where to put gauges actually? If you have limited amount of resources, you would like to put additional gauges, as you said, to send to groups of students or whatever, or install automatic gauges. So that's an interesting problem. It's optimization problem. Where, if you have limited number of gauges to install,
or limited number of students
to lose
in the forest.
Yes, that's right. This is or limited number of camps where to send the students. Yes, so that's also maybe something to think for everybody, because it's often the case. We want to invest into hydrological networks, and we don't have much money, so why not to optimize?
It's a very good question. I don't have the answer.
We have a PhD student who works on this, so if you're interested, and of course other people who also do this, it's about optimization of gauging or sensor networks.
The only problem I see is that you ask the question in a very polite way, or physically hydrologically correct way. You said, if I want to put more gauges, where do I put them? Usually the question we receive is, we want to remove, your network is too expensive. We want to remove 20% or 50%. Which one do you want to keep? And when you are in that position, you are in a defensive position. You do choices which are maybe less well grounded.
Yes, that's true. And could I also connect? That was another thing. Look, you put gauges. Some people say we want to have as much possible of information, as much information as possible. But in fact, our reason should be different. I think we want to solve our problem, for example, flood management, as good as possible. And then gauging could be different. Because we're not interested in information per se, we're interested in assimilating this data in such an extent, to such an extent, that our model would be the best possible model in the end. So that's two differences. they lead to different structures of networks, of sensor networks.
Yes, but again, I see a danger. In France, when I started hydrology, in many regional offices of the environment, we had two gauging networks. We had the gauging networks that had been created by the Ministry of Agriculture. They were strictly interested in low flows, and the gauging network by the Ministry of Public Works, strictly interested in high flows. Again, but this is an illustration of what you say, and I understand that. But if our resources are not that many, and sometimes they were putting gauges very close to each other, I found some just to check all the states checking the electricity company. Okay, so this is a danger.
But in many countries it's the same thing. Yeah. United States, same thing.
Sorry to interrupt, but
no. I'm finished. It was time to interrupt me. No. Is anybody willing to interrupt me, or do you want to interrupt the day?
Could you continue? It's
no.
So interesting.
Oh, I'm so sorry. You are so polite. I know it's a lie, but it's wonderful. It's wonderful.
No, but it's optimization problem with the constraint.
Yes.
And we have constraint which is over there. But of course we want to get more knowledge. Indeed, extremely interesting.
But in fact,
I will leave this presentation, right?
Yes. I agree that the problem is optimization under constraint. And basically when the example I was giving of a slightly gauged catchments with a couple of points, we could have the immediate, if we are used to long-term series to good life, good hydrological life, our immediate let's say reaction is to say, okay, I will extract the information from the few gaugings I have, but there is not enough information, so my choice will be between things that have no hydrological meaning. And one of the constraints was to say, okay, you will choose, but you will not choose in my case in the 4-dimension space. You will choose in a list of parameters. I have an expert that have given those are plausible realities, not realities, it's a model. Plausible parameter sets for the models, and that will be your constraint. So everything is a problem of constraining. And quantity of information. That's all. Finish.